we now describe another geometric problem whose solution comes to us through definite integrals. And this problem, essentially, it takes one of these regions whose area we're able to find, and it revolves such a region around either the x-axis or the y-axis. So let's see exactly what that might entail, and I'll use a specific example. Right? And I'm just going to take the function y equals x squared. Right? In fact, let's make your y-axis a bit longer. And let's say this is from x equals 0 to x equals 2. So that's the portion there. This is y equals x squared. Let me label my axes. Let's go out here a little bit more. There's my x-axis, right? Now I'm not going to shade the actual region, but yes, it's under the graph of y equals x squared from x equals 0 to x equals 2. Now what we're going to do is pretend that there is a crank like attached to the x-axis, and I can turn that crank a full 360 degrees, which is going to take this region and revolve it all the way around. So it's going to look something like this. Let me sketch now after it's revolved 360 degrees around the x-axis. We'll have another border there, and then we're going to have a, so I'll try to give it the sense that it goes around the x-axis like that. And the solid, now it forms a solid, and it actually looks like a part of a trumpet, so you have that big kind of open face right here, and then it tapers off to something narrow right here. And this is what we call a solid of revolution. And these solids are formed, right? So these are formed by revolving a two-dimensional region. So those regions whose area we can find, now we're going to take those regions, so by revolving a two-dimensional, so something flat, so two-dimensional region around some axis. So around some axis. And for us, it's going to be either the y or the x-axis, right? So now we have this solid. So what is the question? What do we want to know about this solid? So our goal is to find the volume of this solid. So what is the volume of this solid? All right. So just like how we had an area problem, this is now a volume problem, and it's a specific kind. There are other types of volume problems. This is the one that we're going to focus on, and there's several variations of this, and we will do it over a few videos. So the idea is this. What we're going to do is try to replicate the process of finding a Riemann sum that would approximate the volume, and then make that sum exact by taking a limit, right? So in fact, we're going to try our best to stick to the process that we know for area and see if we can use it to solve the volume problem. So what we're going to do is this. We're going to start with a partition, and we're going to split up our interval, right? And then, so what I'm going to do, because first of all, it's hard to draw something that's 3D on a flat surface, right? So I'm not going to draw too many things on it, but this interval here, so each interval interval has width delta x. So we're going to use the same delta x as we did from area. So each interval has a width of delta x. And we are going to pick a special x value out of each one. So let's say we were to pick the midpoint. And what we're going to do is from that interval, right, where I have the little asterisk indicated, I am going to slice out of this a disk that goes all the way around. Right, so I'm going to slice out a disk. Actually, let me make that a little bit more clearer. Right, so we're going to slice out something that goes all the way there and then all the way there. Right, so we're going to take a disk out, and that disk is going to have a certain height, and it's going to have a certain radius, and the question is, what is its volume? So now, as far as the radius, you see the axis of revolution right here runs right through the middle of the solid. So the radius is going to extend from the axis up to the curve. Now, I kind of covered up my little blue asterisk there. But if this is the x value that I chose, then the radius will be that distance. So I'm going to write this down as f of x k bar. The same kind of notation that we used for area, but now we're going to try to use it to solve volume, right? So I have this radius of this disk, and I have its width. So let's do this. So I mean, it is really hard to see, again, because of the difficulty of trying to do something 3D. So what I'm going to do is like just take a microscope, and we're going to put this little region under a microscope, and I'm going to draw it bigger over here, right? And this is what it's going to look like. Not only that, but I'm going to rotate it and set this disk flat. So it's going to look like this. It's going to go all the way around, and then it's going to have a little like height to it, and that's going to be based on my delta. So here it's like the disk was on its side, and now I'm laying it flat, right? And then so then the axis would run through like this, right? So now let me label things a lot more clearly now that we can see it. So this right here is your delta x, and it represents you could say either the height or the width of my little disk, right? So this is the height, right, of one of our very tiny disks. And then the radius is this distance here, and that distance is my f of x k bar. So let's label that. So this here is f of x k bar, right? And this represents the radius of the disk, right? Radius of disk. So the question is, what would the volume of this little disk be, right? Well, the concept, so this is really it has a cross-sectional area that is circular, and then it has this linear height, right? So the volume of one of these disks, so the volume, so if you remember your volume formula from geometry, so the volume of a disk, or this disk, is, it would be pi r squared times h. Pi is our, constant, and then the r represents the radius, and then the h represents the height. So let's write this now in terms of our function and in terms of our delta, right? So this gives us this formula. So one of these disks will have this volume, pi times my f of xk bar squared, and then times the height of this disk, which is delta x, right? So the Riemann sum would be the sum of all of these going from k, k equals 1 to k equals n. So therefore, the volume of the entire solid, so the volume of the solid is, so let's write down what the approximation would be first, so is approximately V, and I'll put my little approximate sign, and it would be the sum of all of these expressions, right? So we'll have k going from 1 to n, and then we'll have we'll have pi times the function evaluated at that special x, just like in the Riemann sum, squared, and then times delta x. But if we can say it two ways. Either we let n go to infinity, or we let our delta go to 0. What happens is the solid gets filled in more and more precisely with a lot like thinner, or I guess I should say shorter disks, right? So if we let our delta x approach 0, then we will get the exact volume. So the exact volume is given by, and so it's going to be the limit as delta x approaches 0 of our Riemann sum, right? Which is equivalent to saying that n gets very, very large, right? So either we let our n go to infinity, or delta x get very, very small. This will be our Riemann sums squared and delta x. But then this is how we define a definite integral, by taking the limit of a Riemann sum. And now what I will say is, if the interval is now from a to b, then we can write our volume in terms of this formula. So remember, all of this turns into our integral sign. The f of x bar k, or k bar, however you want to say it, just ends up being my f of x. So I have pi now, and then it's f of x squared times dx, and then this goes from a to b. And this is the formula. Let me write it again and then box it off. This is the formula that's used to find the volume of a solid of revolution when the region bounded by f of x from x equals a to x equals b is revolved around the x-axis, right? So with all that, we end up with a fairly simple formula, right? And let's see how this formula is used. So let's now use this to solve the problem that I started with, right? So now, let's go back. I'll restate it. I remember what we started with. We said take the function y equals x squared from x equals 0 to x equals 2, and then revolve this region around the x-axis and form this trumpet-like solid, right? So, right. And again, you don't have to be able to sketch this. I mean, sometimes I struggle to sketch these things. So here is the solid. Let's find its volume, right? So it's a matter of just applying this formula. So now, we have this constant pi, right, which came from our formula of the disk. And then our function has to be squared, and then we integrate it like we normally do from the lower limit to the upper limit. So our volume here is the integral from 0 to 2 of pi, and now I have to square my function, so it's x squared squared dx. And then, so now since the pi is a constant, in fact, sometimes when you look at this formula, the pi is factored outside. So they might put it outside, which we know we can do. And then before we integrate this, we have to simplify x squared squared. So properties of exponents say to multiply the 2 and the 2. So we will have x to the 4th dx, right? And then find our antiderivative. So it's going to be pi times 1/5 x to the 5th power from 0 to 2, right? So this ended up being a really simple antiderivative. And then our constant is, I'll write this as pi over 5, and then at the upper limit, 2 to the 5th, that's 32, minus 0 to the 5th, which is 0, so our volume is 32 pi over 5. Now because it's volume, it would be units cubed, right? So if units were given, it might be something like centimeters cubed or feet cubed or inches cubed, whatever the units is, because it's volume, it's now a three-dimensional measure, so you have your units cubed, right? So this formula that we found by using the disk approach is called exactly that. So this is the it's another famous formula. So this is the volume by disks method, right? Now, and it turns out that this method also applies to regions that are bounded between curves and the y-axis. Because if you remember, when we did area, we looked at it with respect to x and with respect to y. Well, the same thing could be applied to the volume question, right? Or this volume problem. We could be looking at the region, instead of the region going from the curve down to the x-axis, it could be going from the curve across to the y, right? So let's make a statement about that and just essentially draw a sketch so you see what happens, and then do an example where the integration is with respect to y. So here we go. So similarly, if the region is defined by a function, now let's say x equals w of y, right, for y going from C to D, right? And so let me sketch that, do that over here. So now we're saying that x is a function of y. So you might have something that looks, let's say it starts here and then it just kind of goes up like this. And so now the curve here is x equals w of y, and it starts at a lower limit of c and it ends at an upper limit of d. And now let's say we revolve this around the y-axis, right? So because the function is in terms of y and the limits are in terms of y, it seems like a natural way to revolve it around the y-axis. So then the solid looks like this. So it will have pretty much the same distance here on this side, and then it's going to go up like this. So my solid looks kind of like that, going around the y, right? So that would be my solid. And again, the question is, what is its volume? Well, we can use the exact same disk approach, right? It's just that now the disks, instead of going around the x-axis, they would go around the y. So one of these disks would look like this, and then going all the way around, right? And then we would be finding the volume of one of those and then adding them all together, just as we did in the Riemann sums, right? So if this is now the problem, the disk method also applies. So the disk method also applies and produces this formula. So produces this formula. And you take the pattern, so the volume will be the definite integral now from C to D, and my function is, it'll be pi, but now it's going to be my w of y squared, because it's pi times the function squared, and then we integrate that with respect to y, right? So that is the disk formula when you have a function in terms of y, your limits are in terms of y, and you're revolving around the y-axis. All right, one last example. So let's say, so here's another example. And how would something like this be worded? So let R be the region bounded by, let's say it's the equation x equals e to the y, right? So notice again, we're expressing x as a function of y. And the y-axis, right? So it's bounded between that curve and this axis over the interval. And let's say this one goes from 0 up to the natural log of 3, right? So that's our region. What is the volume formed, right? Or what is the volume? So what is the volume of the solid formed by revolving R, this region, about the y-axis. So about the y-axis, right? And this one again. Now, in terms of sketching this particular function, it's going to look similar to y equals e to the x, but it's like you have the x and y axes switched, right? So it would look something like this. Right? So let's see, so y goes from, so y equals 0 is right there, y equals the natural log of 3 is right there. Notice when y is equal to 0, x is equal to 1. So right here, so it starts here, and then when x I'm sorry, when y is equal to the ln of 3, x is equal to 3. So it's out here. So, and then it has that exponential shape like this, right? And then that means the region, let me shade this in a different color, so the region is right here. And then this is now revolved around the y-axis. So my axis of revolution is right there, and then the other piece comes out like this, and then it goes all the way around and forms this solid, right? Almost like a funnel, but again with a very wide base, right? So we want to find its volume. So by the disk method, right, it says the volume is, so you take the integral, and the integral goes from the lower y to the upper y. So those are my limits. And the formula is pi times the function squared. And this function is e to the y. So it's e to the y squared dy. And let's evaluate. So again, we can pull out the pi because it's a constant multiple. So we have pi times the integral from 0 to the ln of 3. Now this simplifies to e to the 2y. Again, when I multiply those two exponents, that's how it simplifies. And then I have to write down the antiderivative of this. So we have to use our special exponential rule. So it is pi times the antiderivative of e to the 2y is 1/2 e to the 2y, and then we evaluate it at 0 and the ln of 3. Now for the constant in front, I can write it as pi over 2. Now at the upper limit, I'll have e to the 2 times the ln of 3 minus e to the 0. Now both of these can be simplified quite a bit. In order to simplify when we evaluate it at the upper limit, we first have to apply the properties of logs and take that 2 and make it the exponent of the 3. So it's e to the ln of 3 squared. And then of course we know e to the 0 is 1. And then, because the exponential function and the logarithmic function are inverses, I'm left with 3 squared, which is 9. So it does simplify quite a bit. I still have my pi, so it's still going to be irrational, but at least we'll end up with just 9 minus 1 there. So that's 8, and then 8 times pi over 2, it's 4 pi, and then this will be units cubed, right? So the disk method, it works well either if it's a revolution about the x-axis. Now if you're revolving around the x-axis, you need to make sure that your limits are on the x-axis and your function is in terms of x. Similarly, if you're revolving this region that goes from the curve all the way across to the y-axis, then you have to make sure, again, your limits would now be in terms of y, and your function would be in terms of y. And then we apply the disk formula. So it's a fairly straightforward method. The only thing that can throw a wrinkle in there is if you end up with slightly harder or more challenging antiderivatives. But once you've recognized, whether it's with respect to x or with respect to y, once you recognize that your disk method applies, it's fairly straightforward. Just do your antiderivative and all your algebra carefully, right? And in the next video, we'll continue looking at the volume problem and looking at several variations of it. See you then.